Good evening, all of you. Welcome to the fifth and the final day of our workshop on AI and robotics. So today we have a very distinguished guest, Sri Jayan Gandhi sir, who is affiliated for the past 23 years to Regional Science Center and Planetarium Calicut. He is the officer in charge of the Innovation Hub at this center, which is organizing this workshop in collaboration with IIT Kozhikode Sub-Center. And he is instrumental in design and development of various scientific as well as technology-based programs and student projects at UG and PG level undertaken at the Innovation Hub. Development of science galleries on contemporary scientific themes in Science Center, astronomy and astrophysics related programs for the Planetarium Division. He was deputed by the National Council of Science Museums, NCSM Government of India, to Guangzhou, South Korea as a team leader in International Astronomy Olympiad in 2011. He has published several articles, papers and manuscripts. He is presently working in the capacity of technical officer. He has obtained his MSc from Alagappa University, MCA degree and postgraduate diploma in astronomy, astrophysics and planetarium science from BIAPS. He is also associate member of Institute of Electronics and Telecommunication Engineers. He has also academic interest in discrete mathematical structures and computer science and applications. So a warm welcome to you, sir. The IC is all yours.
Thank you, Joel, for a good introduction. Now let us start the presentation with a short video.
That's a little too close for comfort, lady.
Oh, damn.
What, you never seen a talking gargoyle before? Welcome to Illuminati headquarters. I mean, Denver International Airport.
This is awesome.
Hello? Do I know you?
Are you hungry?
Oh, I'm starving. You got anything for me? Those flowers look delicious.
Oh my god!
Oh, it's because of the conspiracy.
Oh, it's because of the conspiracy. Look at me. I'm a little know-it-all. Will you get back over here? I got a question about this conspiracy. Did you have to buy an extra seat for your hat, sir? Sir, are you stealing a desk? Sir, you have resting, confused face. Do you have a favorite animal or pet?
A caterpillar?
A caterpillar? Wouldn't you rather have a gargoyle?
No!
Yes! You know, you can actually put the phone down and have a conversation with me. But no, I'm a millennial. I've got to post it. I've got to snap face it and Twitter book it. Excuse me, miss, I've got a stain that needs some polishing. Can I borrow your cleaning cart?
Oh no!
I need your help. Guess what my favorite food is?
What?
No, I want you to guess.
Human?
Cumin. Yes, I love cumin.
I said human!
Oh, I thought you said cumin. I'm a real big spice guy. Furry hat guy. I can't believe you are wearing one of my friends.
Hey, this isn't your friend.
It used to be until you put it on your head, man.
How old are you?
Well, 243 years old now. I look good for my age, don't I?
Yeah, you work out?
All the time. You should see my squats.
You're such a sweet talker.
Will you take me back home with you?
Let's go. I have some space in my backpack.
Actually, I think you have too much baggage for me.
All of you, what do you think about this video? What did you also? Can you just reflect upon it?
So what I feel is that the upper part of that gargoyle's face was actually modified into a robotics part, and then it was inbuilt with some chips for artificial intelligence, which was able to have a camera to see the outside things, and then have machine learning to adapt itself around.
Hello, sir. It's always something related to artificial intelligence. According to the behavior, it is easily related to human behavior. When we see the conversation and all its behavior, it's able to sense all the things what is happening all around.
So now let us see. Now there are some of the views which all of you have, some of you have actually expressed. But then one thing you can understand that there is a very complex. This is good from a certain point of view, but when we interact with the fellow humans surrounding us, we take many other cues into things, and there is a way actually which the surrounding, the situation surrounding us has a representation. We have a knowledge about the surrounding on which we ultimately react and which we behave. So let us see how this knowledge is having, how people are trying to represent this knowledge in the field of artificial intelligence.
Let us see how the knowledge representation or what is the knowledge. So when we come about, when we speak about intelligence, so intelligence is a variety of things. Intelligence is nothing that you are coming, somebody comes first in an exam, or it is nothing to do with only academics. There are a lot of different types of intelligence. In fact, nowadays people are speaking about emotional intelligence also, and there are somebody is intelligent in doing an acting, somebody is intelligent in making a good piece of art. So generally, actually, with a very vague, very broader definition, we can say that it is something to do with the faculty of understanding. So what is that understanding? What is the concept of understanding? It is something to comprehend something and to recognize its significance. The significance is quite important here. So we know that for being intelligent, we require certain knowledge. Now, what is knowledge? Knowledge is the facts around the world. That is what is the facts with which we interact. We have to know those facts to interact. So that forms the knowledge. The knowledge, there are various properties of knowledge, like it is huge, it is going on increasing. Day to day, every day, we are getting lot of knowledge in which we correct our beliefs, we revise them, we get new concepts, we understand new things. So knowledge is always, it is having a big volume, it is hard to characterize, it is changing, and it is not data. The data, see, your hard disk has a lot of data, it can't do a lot of much with those data, so it is something different. And what is machine intelligence? When we speak machine intelligence is something like we want our machines to do some things which we otherwise would have felt that human would have done it. So this is why. So I don't know whether you have known about Alan Turing. He was actually a scientist, mathematician, logician. He was a great personality. He was a computer. He himself was the first person to think about intelligent machines. So he has devised a machine called Turing machine, and on that machine he has devised something called a Turing test. So what is a Turing test? A Turing test is something, see, there are two compartments, two isolated compartments, and nobody knows in which compartment there is human and in which compartment there is a robot there. And without knowing these two, a third party tries to interact with these two compartments, with these two persons which are in those two compartments, without having any idea about which compartment has the robot and which compartment has the human being. And if it happens that this person actually could not recognize in the full procedure of interaction, he could not recognize and distinguish between a human and a robot, that machine is actually said to have passed Turing test. Until today it has not passed. Many have gone to a greater degree, but it is still today not actually completed. So intelligence as such is a difficult concept to define. It is a multifaceted thing, and we will see. So the key issues with artificial intelligence design. What are the key issues? Key issue is knowledge acquisition, how the knowledge can be acquired. That is knowledge representation. We will see about this representation. That is one of the major part of this presentation today, how knowledge is represented and how knowledge is manipulated. Why it requires a representation? Because it has to be manipulated. In fact, we ourselves don't know how the knowledge is represented in our brain or in our mind. We don't know actually. People are trying to do a lot of work in brain science, and in fact today there is a faculty or there is a discipline which thinks about, which works on brain inspired computing. So how our brain works, based on this they are trying to model the machines, and they are trying to do that. So that is one of the frontier areas of research, and a lot of people are working on it. A lot of money is going on that particular research. The field of knowledge engineering can be defined as a process of accessing the problem, acquiring knowledge, and building knowledge bases from that. So this is a different discipline which is coming up. So let us now go through each and every of the subparts. We have seen in the last part that there are two issues. One is that it is knowledge acquiring, knowledge representation, knowledge manipulation. So what do you mean by knowledge acquiring? So we have to identify what is the knowledge domain. from where we get the knowledge. What is the domain? We'll speak about it. And locate knowledge sources. What are the sources from the knowledge? Because when we, for example, experts knowledge, for example, a chef makes a very good dish. You like it very much. But is it just that what type of ingredients he puts makes it the dish so delicious? Because then everybody would have made. There would not have been a particular chef. There is an actor who acts so well, and we appreciate that. But then if his knowledge is so easily, precisely represented, precisely understood, then anybody else could have been transformed with that knowledge, and they could have also become the same actor. But it doesn't happen in that way. Similarly, we have a lot of other fields where actually the knowledge location, knowledge representation, the overview of the domain, its boundaries, how its rules are there. We will speak about this, how the rules are applied. What do we mean by rules? I will explain you in due course. And the knowledge base, the domain of the knowledge base that is formed. So this all constitutes what is called as the knowledge acquisition. Then sources of knowledge. What are the different sources of knowledge? Normally when we take any particular discipline, for example, we go and some of the major sources are literature, because like journal papers, good books written by original authors. So like that, these are some of the somebody who knows it very well and have done a lot of examples out of it. So these are actually the main sources. And there are other bases also for knowledge, like scientific laws. People are discovering new laws. From that, we discover new insights. Then experimental models, physical experimental model, data analysis model, or simulation model. These all helps us actually to acquire new and better sources of knowledge. And these are the sources of knowledge. And then what are the components? How actually knowledge is bifurcated? Knowledge. What is knowledge? We have given a vague definition, but with that actually you can't do anything to represent knowledge, to make a machine understand knowledge. You have to characterize it. So how do you do that? So knowledge consists of actually facts, certain procedures, certain judgment rules, certain way of dissemination of this knowledge. So these are all actually to be understood, and a lot of people are working on a lot of different aspects of this to make a system understand how actually these different forms of knowledge can be utilized and the way it has to be done. So there are these types of knowledge can be actually perpetual knowledge, perceptual knowledge which comes through senses, sensory, or which can be at least indirectly changed to senses and relationship. So they are perceptual knowledge. Our perception is through our eyes, through our all the sense perception. It can perceive through infrared rays and convert it to certain electrical signals which we can understand. It can perceive through ultraviolet rays, and so we have the full electromagnetic spectrum of perception today available with us, and with all this actually we get new knowledge. That is the reason actually this, for example, astronomical knowledge. We know the universe in all multi-wavelengths, so there is multi-wavelength astronomy. So those are there. Then there are strategic knowledge. See, what one particular problem is there between certain community or certain countries, and certain it is not a very straightforward way that the problem can be solved. You go and set the procedure and it gets solved. There are certain strategies which are used. There are these forms actually strategic knowledge. So how to define the problem, how to go about the difficulty, and come out with a solution. So they are strategic knowledge. So knowledge representation is how to encode. So all these types of, from various sources we got knowledge, we have represented knowledge, and we want to encode this knowledge so that machine understands the knowledge, interprets the knowledge, infers from the knowledge, and gives us output the way we want it to be. Because for us, the most standard way, as per our understanding, we humans, some of our humans have achieved great height, and we humans, the way we understand, the way we feel, the way we interact with others in different situations, we change. In fact, in an interview also, if you go, the way the panel is asking questions, your behavior will change. So all these things are very complex systems, and there are a lot of knowledge interaction, lot of knowledge interchange are occurring there. So all this has to be represented, and an intelligent system should be able to work intelligently with all these representations. So there are structuring, processing tool like knowledge bases, inference engine, and some we will see all these things. So what are the parts of knowledge representation? There are certain objects in the world, there are certain events, Any event mean anything happening. Your flash of a light is an event. Your eating of a chocolate is an event. Your seeing a movie, you're cracking a problem is an event. Everything is an event. The performance, the way the event is performed, the meta knowledge, that is the knowledge which is not visible to you, but without that you could not have done this. So that is called meta knowledge. Facts, the representation of facts, the knowledge level, the symbol level, all these things we will see. So these are the parts of knowledge representation, and these are this is the way actually knowledge is represented. So knowledge representation, there are the various two distinct form of representation. One is that for a machine to understand, the machine works via certain voltages, because that is the way we conventionally certain states of certain devices. So we have to represent our knowledge in that particular way. So representation involves symbolic. First, we have to have a good symbolic apparatus to transform the knowledge into a symbolic domain. So that is very important. And then we should have certain solution techniques, certain procedures, certain ways of storage and retrieval. So these are very important things. See, we have all of us study lot of things and go to an exam. Okay, but all of us don't reproduce in the exam in the same way. Why? The question is why all of us don't come first. Some gets 99%, some gets 100%, some gets 60% and below. So why this happens? Because we all may have not understood the problem. We may not have got retrieval of this knowledge which we have acquired. So all these things fail. So our machine, we want the machine to be smart. So all these things has to be taken care of for a representation of knowledge, so that it can be used in a certain proper way. So properties of good knowledge representation. So makes, for example, make the objects, important objects and relations between the objects. There are constraints which has to be maintained. For example, when you are speaking to a principal of your school, or when we speak to our bosses, we will not speak as if we are speaking to our classroom friends. So that form of constraints are there. So these are not only so. There are various other things also. So then there are certain irrelevant facts which has to be eliminated before we make a good representation. It should be transparent, it should be complete, it should be concise, it should not have so much noise in the knowledge, so that irrelevant information, irrelevant things associated with the knowledge, and it should be computable. So all these things, everything is not computable. That we will also learn in due course. And if it is not computable, the way actually our brain computes, we don't know. We don't know how our brain computes different knowledge, or what are the representation procedures. There is also a lot of research going on in computer science, philosophy, mathematics. A lot of people are studying a lot of things to understand how actually the knowledge is represented in our brain. So that is also not known much. So all these aspects has to be taken to make a properties for a good representation of the knowledge. So logically, what is known today, what the status of what is known today is actually there are few procedures which are used for representation of knowledge. There are different categories. One is the logical representation scheme, formalized symbolic logic and critical calculus. So we will see about it. We will go to a fair details of that, because today's presentation is on those types of logical representation. And there are certain other people have tried to represent it in a different way, like procedural representation, like rule-based expert system, which works through certain types of logic. Then there are networked representation, like semantic networks, where we create objects as nodes and inter-nodes relationship. So the node relationship or conceptual graph, and all those types of things that we will be seeing. And then there are structured representation like frames and scripts. So there are variety of ways people are trying to attack this problem, and in future maybe newer schemes will come up, and newer ways of this knowledge representation will be coming up, and we may be able to know more about these types of representation, because many things are not known. So before we actually go for each of these, let us take a brief introduction to all these representation. So let us take the logical representation scheme, that is the formalized symbolic logic and predicate logic. So formalized symbolic logic. So how many of you, just unmute your mic, how many of you are exposed to this logic? How many of you have actually studied something about this logic? Anybody has studied in this group who are participants who are there? Anybody? You can open your mic and tell, or you can put it in the chat box. I think you can see the chat box. Yeah. So see. Anyway, there is nothing that you need to know about this logic. We will be introducing this just now. This is one of the basic things in which a lot of people are working in India, in abroad, and people are working. For example, we have a lot of institutes. We have theoretical computer science functioning in their departments, and people are studying those things too. They are mainly working on logic only, and that is a part of that is a very big part of the artificial intelligence team, because knowledge represented, you can make a lot of mechanical things, you can make a lot of with movable parts and all, but ultimately the knowledge is the main thing which will drive the thing, okay, which will respond it with the surroundings. So that is very important. So let us so what is a knowledge is formal method of reasoning. If I just give you the definition, you may not appreciate. I will give you something. So let us actually move to the board. Let me move to the board and let me try to illustrate you with that particular thing. So just come there. And you can always ask me whenever you are not following certain things, and I will be describing you certain things. Now, when we speak about propositions, what is a proposition? Proposition is that my name is Jan Ganguly. Jan Ganguly is a person who is working in Regional Science Center. Jan Ganguly is a person who is interested in computer science. So, see, these are all actually facts. We say about facts. A proposition is a fact. So, for example, we have Jan Ganguly is from Calcutta. He is working in Regional Science Center, Calicut. He at present is staying in Kerala. So, all these are facts. Now, we can actually represent all this symbolically. Okay. So, so this symbolical representation will come to it. So, these are propositions. And there are certain things called predicate. Now, what is a so when we speak in a proposition or a sentence, an English sentence, when we speak propositions in the form of, say, we speak about certain objects. So this is a good cake. This is a good table. So we are speaking about the table. The table is the object, and the thing which is making it to speak about the object, that is called the predicate. Okay, so predicates speak about the object. So we will see all those things. So propositions are actually so we can represent proposition symbolically like P. P say let us represent it as, what does P mean? P means that say Jan is working in Kerala. Now this is a proposition I have represented with a symbol P. Let us take another proposition Q. So it is Jan is from Kolkata. Okay, so this is another proposition. So like that you can go on writing a lot of propositions. So I have represented this full proposition with a symbolic symbol like P and Q. So these we do it when we do algebra and all, we represent it. Now, now these types of propositions, we have to define certain types of apparatus with this. For example, if P is representing that Jan is working in Kerala, then there are something like not P. This is called not P. Somebody likes it as like this, not P, or you can place this as here also. This is called not P, or this is called not P. All these are called no. So these are negations. We have negations. Okay, so negation. So what does this negation mean? Jan is not working in Kerala. So P means Jan is working in Kerala, and negation of P just means that Jan is not working in Kerala. So similarly, we have conjunction. Say so this is called negation. There are certain things like Conjunction. So, like we use another symbol like here. This is called conjunction. So what is conjunction? Conjunction. So conjunction means that the Jan is working in Kerala and Jan is from Kolkata. So this can be represented very easily by symbolically by using this particular fact. So this is called conjunction. So conjunction is there, then we have disjunction. Like if if disjunction is between two particular proposition, so either this is correct or this is correct. So proposition basically is either true or false. It is a fact about a world which is either true or false. This is like Boolean logic. It is a two valued logic. It is either true or false. So Jayant is working in Kerala. It is either true or false. In this case, it is true because I am working in Kerala. Jayant is from Kolkata. It is either true or false. So it is true. A statement can be either true or false, but ultimately its value gets fixed. Either it should be true or it should be false. So that is the way actually. So we have here negation is there. This is called conjunction. This is called disjunction. And then we have exclusive disjunction, which is something like this, or it P or Q, or it is also represented as like this, P or Q. So that is a disjunction exclusive. So in that P or Q means either both of them, both the statements are true, or one of the statement is true, other of the former is true, other is false. Other is true means the former is false, other is true. So in all the cases, this disjunction gives a truth value as true. But if it is exclusive, so only when either of this that is true, actually these statements become so. So these are actually these types of things like conjunction, disjunction, and negation. These are all operators or logical operators in this two-valued logic. That is, and every statement is a proposition. Every proposition has a truth value. A truth value can be either true or false. So based on all these concepts, we have different types of truth values. So let me illustrate those truth values before we. So how do we check it? So these types of knowledge. So once we know these types of knowledge representation, we can speak further. Then only we can speak about other types of knowledge representation. Let us start. So if you have in between any questions, you can always talk. So we have truth values. Let us see the truth values of different types of things. We have, for example, negation. So we have a proposition P. So we have P here and say not P. So either if P is true, not P is false. If P is false, not P is true. So this is the truth table or truth value of the proposition P. Similarly, if we have for the not, so we have P and P. So if we have P one proposition, Q another. So we have P one proposition. If you can't see, you should tell me. Otherwise, I will not know whether you can see or not. So if you are not able to see, you should tell me. So let me write it here: P and Q. So either see. So how do we write? So we write P, we write Q, we write P and Q. So we have conjunction. So we have this is true, P and Q is true. So either of them is false. This is true, this is false. So then again, this becomes false, this is false, this is true, this becomes false, this is false, this is false, this becomes false. So this is the truth value of conjunction. So P
might be logical operators.
These are logical operators. Okay, two-valued logical operators. So you should know that. Only we are speaking about truth values in two cases. So then we have P or Q. So what is P? Then we have P, Q, P or Q. So this is true, this is true, this is true, this is false, this is false, this is true, this is false, this is false. I said that P or Q. So either of them is true, then it is true. So obviously this becomes true, this becomes true, this becomes true, this becomes false. But then we have in this case P or Q means both are true, it is true, both are false also. Means either of them, so it is not strict. So in that case actually we have other one here which is called exclusive. So we have truth value of exclusive in this particular way. So we have P, Q, P, Q. So we have truth value true, 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 false, false, true, false, false. So true is false. So only if either of them is true, it should be true. So these are the true, this is false. Okay, so this is the way actually we make the truth values of or either or. And the order of the precedence when we are given, for example, all these truth values are coming together, what is the order of the precedence is that negation comes first and it goes in this particular order. So that is very important. Okay, so this is actually like combining the truth values. We have either P or Q, P and Q, exclusive P and Q, and negation of P. Now, when we want to make inferences, because I said you about inferences, when we are speaking about inferences, how that thing happens. So let us see about something about inferences, which means implications. Let us go to that. So there are some conditional statements. We know when we do other things like programming and all, we have studied about conditional statements. So let us see conditional statements. So if P happens, P implies Q. So it is something like so if you get the truth table of conditional statement, it becomes like P, Q, P implies Q. So if you have true, 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 false, false, true, false, false. So in this case, actually we have this is true, this is false, this is true, and if both are true, this is true. This is the truth value of the conditional statement. So what is that? If P is called the hypothesis, this is called the hypothesis, and this is called the consequent. So hypothesis and consequence are so if this happens, if P happens, it will imply Q will happen. If there is cloud in the sky, there will be rain. There is possibility or there will be rain. If there is sun in the sky, it will be hot. So like that. If something happens, if the fire is on, we will get light. So like that. P implies Q. So that is the way actually the conditional thing occurs there. So there are a few things to be noted here. When we are these are so we have converted the known facts into symbolic apparatus, and we are developing certain symbolic apparatus. Like so we have said about P implies Q. Now there is one more rule we can put, that Q implies P. So when we already have P implies Q, what does Q implies P means? Q implies the converse of P implies Q. Converse of P implies Q. Then we have if P implies Q, we have not P implies not Q. So if there is rain, if there is cloud, there is rain. If there is no cloud, there is no rain. So this is something like this. It is there. And then we have contrapositive, like if there is, if in other way, if it is not Q, implies not Q. So this is the thing about contrapositive. Then this is about implication, which goes in one particular direction. Now let us see about biconditional, how biconditional things work. So we have an hypothesis and we got the consequent, and the way it works I have shown you. Now let us just move to the biconditional way. So biconditional, so it is represented as something like in this way. So what is the truth table for biconditional? P, Q, P biconditional Q means both are true, one is false, so first is true, second is false, first is false, second is true, both are false. So when both are true, it is true, and when both are false, that is also true, and then other things it is false. Okay, so what is the significance of this? What it means is that P is the necessary and sufficient condition for Q to occur. So that is the interpretation. So all this have interpretation. P is the necessary and sufficient condition for Q to occur. See, P implies Q. So P implies Q. Something else can also implies Q, and Q can be resulting. Q can be a result of something else also. But in this case, actually, both are required, and one is sufficient for the others to occur. So that is the catch in these two things. And there are certain well-defined rules which can be tested using logic, using all these whatever we have discussed just now. So I will just mention it for the completeness. So they are called. So let's do one of them. We know it, or you also know it. Actually, it is called De Morgan's law. What it says is that not of P or Q is equivalent to, okay, by conditionally equivalent to not P and not Q. Not of means negation of P and Q. P and Q or conjunction of P and Q. This is negation of disjunction of P and Q is negation of P, conjunction of negation of P and negation of Q. Disjunction of P and Q, negation of disjunction of P and Q is negation of P, disjunction of conjunction of negation of conjunction of P and Q is negation of P, disjunction of negation of P and negation of Q. So this is the famous De Morgan's law. And there are certain facts that which is always true. Fact is always true. Something like the earth moves around the sun. This is a true fact. It is always true. At least for the next some few thousand years, or we don't know, it will be true. So when a statement is always true, it is called a tautology. And when a statement is never true, like a winged horse, it can never happen. A round square, it can never happen. Such is actually called as a contradiction. This is a certain thing. So tautology are always true. And it is a contradiction always false. So when a statement is always true, it is called a tautology. When a statement is always false, it is called contradiction. So there are certain associated rules which are used for the inference. So which I am doing all this because I want to give you a flavor of the proposition logic, because when a knowledge is actually transformed into propositions, that we have to do for any real world thing to be fed into a computer, the knowledge has to be actually symbolically transformed. So I can symbolically transform any knowledge into a proposition. You can do it. You can take any paragraph in a text, and you can start different types of objects associated with it. You can take it, you can start to make propositions out of it, and you can make a symbolic representation of the full thing. So that you can do it. You can try it in your home. That is quite interesting. So now we have some good logical equivalence. So we have some, what are the logical equivalences? We have commutative law. So what does it say? P and Q is biconditionally equal to P. Conjunction of P and Q is biconditionally equal to conjunction of Q and P. Similarly, disjunction of P and Q is biconditionally equal to disjunction of Q and P. So this is commutative law. Then we have the distributive law. Which says that conjunction of P with disjunction of Q and R is biconditionally equal to conjunction of P and Q, and its disjunction with conjunction of P and R. So you can reverse it also. P disjunction of P and Q, P and say Q and R, Q and R, which is biconditionally equivalent to P disjunction of P and Q and P Q and R. So like this. So this is called as distributive law. So we have distributive law. Then there are something called idempotent law. Idempotent law, which says that P and P is biconditionally equal to P, or P or P. P disjunction of P and P is P. So these are idempotent laws. So we have, so like that you have a lot of laws and lot of things. So and one more thing is that we have studied about the implication. This operator implication. So can we represent this in form of a using conjunction and disjunction and negation? Can we replace this? Because conjunction, so if you want to reduce, for example, when you are working on a computer set, there are a lot of instructions. Your processor has to follow a lot of instruction. Initially, the processors were developed with that, but then they had to reduce the amount of instruction in the processor, and they formed the new architecture called RISC architecture. Why? Because if you have lesser number of instructions, and with that, if you have to, you can do lot of different works which you wanted to do, and that saves a lot of time. So in that way, actually, if we can convert many of these connectives into few connectives, so that transformation is also quite important. So in that way, actually, people have done this this particular type of thing, which is called an implication. What it is say that P implies Q. This can be biconditionally made, not P or Q. So this is a very famous biconditional statement, and which can be used in other things. So we are saying that also. So now what we have done is that we have explained certain operators. We have explained certain way of converting worldview into symbolic language. So that is what we have done. Now we require certain inference rule to work with them. So that is one of the things which is quite important. So what are the inference rules? So there are various rules of inference, and some of the important rules. So when you have a lot of propositions, a lot of operators working, so how do you make conclusions from a given? Like for example, you have the Euclidean axioms. So how do you make the results which we get it? So that is also the rules of inferences. rules of inference. So one rule is that if P implies Q, if P implies Q, P, that means P is implying Q, P is correct, then we conclude Q. Okay, so this is one of the rules. And what is this rule called? This is called modus ponens. So ponens, P-O-N-E-N-S. Okay, so this is a very important rule. And then we have if P implies Q, not Q, we conclude therefore not P. So this is also one of the very, very important rules. It's you can check it with the truth table, but it follows logically. See, P is implying Q, Q is not, Q is false. Therefore, P has to be false. So that is called modus tollens. Okay. So this is one of the rules. Then we have some other type of rules. Let me write it with a different color. It is like we are given P. We are given P. So we can write P this junction of P or Q. For example, apples are round. Okay, we have done apples are round and they are red in color. Okay, so we can always add attributes to it, provided that is correct. So if it is, so in that way actually, so this is called actually generalization. You are generalizing. Generalization. And then we have P and Q. If this is true, therefore P. Therefore P. That means that Jayant is working in Kerala. Jayant is from Kolkata. So this is true. Therefore, Jayant is working in Kerala is true. So this is called specialization. Okay. So these types of there are. Then we have. I will go on with some more rules. I'll just give you. I'm stating this because you should have a taste of what are the different types of inference rules through which actually this logical inferences. If you know it, that is fine. You can revise. If you don't know it, you can learn. So we have like P or Q, therefore not Q, which implies not P. Okay, P or Q, not Q. I'm sorry, not Q, therefore P. So P, either P or this P or Q is true. It is known fact that Q is not true, therefore P is true. Because this or that, other one is not true, therefore this is true. So this is called elimination. Elimination. And then we have P implies Q, Q implies R, therefore P implies R. This is called transitivity. This is a very famous, in many mathematical things we use it. Transitivity. And then we have P, so these are all there. Then we have, let me write it with a different color. Then we have that P and Q, and P implies R, Q implies R. Okay, so P and Q, P implies something, Q also implies the same thing, therefore R. Okay, both P and Q is there, P is implying and P and Q are implying the same thing. So this is called proof by division. So we have all these things, and we have conditional proof like P and Q. P implies Q implies R. If this happens, P and Q, P implies Q implies R, P and Q is there, therefore R. So this is called conditional proof. Okay, so these are actually various inference rules which are used. So like that, lot of inference rules are there. So you can, as you can see, why this discussion was there, that we have represented knowledge base symbolically. That is first requirement. Second requirement is that we have defined certain operators which can make the knowledge base more compact, because we can represent different facts as a single statement. There are a lot of statements, we can compound them together to form single symbolic statements. And then when we have a lot of symbolic statements, what happens is that we can inference from that and make deductions. So these are logical deduction, but only one thing you have to see, that everywhere actually we are using a pi-valued logic. That is, either it is true or it is false, and this will be challenged in the end. So this is one thing. So now let us move forward. Any questions up till now? Anything anyone you want to know before we move forward?
No, sir.
Okay. So let us move. So next thing which we will be needing is something called set theory. I know all of you or most of you should know about set theory. I'm not sure if somebody is there who doesn't know. So just for completion's sake, because we will be needing set theory to a large extent for today's discussion, so I will just have 5-10 minutes dedicated to sets. So what are sets? As we have studied from long, that sets are collection of objects, say fruits, orange, apple, banana, they form set, a set of fruits, set of places, Calcutta, Kozhikode, Delhi, Bombay, Kerala, so they are set up. So we have sets. So sets can be represented in different forms. So they can either be tabulated together, or they can be represented with representation of a certain rule that is called the set builder. For example, we have a set can be represented by capital letter. It is collection. So we can represent it, say A, E, I, O, U. So we have set. So then we have so this can also be represented as something like X, such that X are vowels of English alphabets. Okay. So these are sets. So when we speak about sets, these are the two forms of representation. But when we speak of a set, we speak of the set with respect to certain universal set. Universal set means it contains everything, like all the samples. When you work in a laboratory, or when you take a group of people, or when a group of students, when you take, we take it as a sample. But then the sample belongs to a larger group, which is the total. Group of students means it belongs to a particular college or school or university. So for that particular university, the students of that group belongs to a totality of the students, that is called the universal set. Similarly, for any sets we define, we should have a universal set, and that is called the universe of discourse. So normally it is represented as U. Okay. So then we have any part of the set. Say for example, for any set, one set is common, which is called a null set. Null set is a norm. Null means nothing, but it is a part of all the set. Okay. So null is there, and if for example we have say a set C, so that A, E, C contains these two letters. So you can see that a part of the elements of the members of this particular set belongs to this set. So we say that C is a subset of A. So we read it as C is a subset of A. And in other way we can write is that C is we can write it something like a subset can be written in this way. There is something called a proper subset. If all the elements of C doesn't belong to any other set, only of this, then it is called a proper subset. And then in this case also we can write it as A opposite way. These are the common symbols. We say that A is a superset of C. So these are the things. So there are certain other things like the complement of A. So what are not in A? Complement of A is whatever is, so instead of writing complement of A, let me write complement of C. complement of C are all those elements which are not in C. But we know that if we consider C to be the universe to be, we can choose our universe. Okay. So complement of C means, for example, if you take all the alphabets, so we can write either we can define if the universe is U, that is set of all alphabets, So this is very important with reference to what we are speaking. So set of all alphabets. If you write it in this way, then the complement of C represents X such that X does not belong to C and X belongs to universal set. So we can write it in this way. So if we define that A is the universal set. So we are only speaking with respect to A. Then complement of C becomes, we have C as AE, so IOU. So it represents what is our universal set of discourse. So that is it. Now we have actually, let us say, have two sets, say A, say 1, 2, 3, and we have another set B is equal to say 4, 6, A, 1. So what is this is A, okay? Let us call it A. So what is union? So union of A is something like what is common, what is available in both A and B together. That is called union. So we write it as 1, 2, 3, 4, 6, 8. So 1 is occurring twice, we will just represent it once only. So that is called union. And what is the intersection which is common between A and B? That is called intersection. And in this case, you can see that only 1 is the common set. So we have 1 is the common set, which is belonging to both. Of course, null set is there. Normally, that is not represented in this particular fact. So this is about algebraic representation. So there are various ways of representing sets. So one of the very favorite ways of representing sets is through Venn diagrams. So we have, say, the universal set is normally designated as a box. And if you have a set A here and a set B here, so it can be, it may not be circle, it can be of any shape. Since it is conventionally put as, and it need not be 2, it can be many, as many we require. We can have a set C also here, which is not related. So what is the union of A and B? So union is represented if you shade everything together. So this is union. Okay. What is the complement of A? So if you have the same scenario, this is the scenario which we were speaking, A, B, C. What is the complement of A? Complement of A because whatever is outside it. As I said, you that universe of discourse is very important. So this is called a complement. So what is A intersection B? We have. So these are some visual tools which can be used to understand to a certain degree only. You can't go on making circles or things. But this is the intersection B. So we have union, intersection, complement. All these things are there. A intersection B, A union B, A complements, and so on and so. So that is the thing which has to be understood about sets. So we have, and then we have a difference of sets like if you have A minus B, what does it mean? The elements belonging to A but doesn't belong to B. So we have something like A minus B means take out full B from A. What is remaining is that this is A, this is B. So what is remaining is here. So that is called A minus B. So and similarly we have symmetric difference that it doesn't belong to. So it is called something like that. That whatever is outside both A and B. So we have like that lot of things. So based on all this discussion, one thing is there. See, an element, for example, when we define a set, then element either belongs to set or doesn't belong to set. So that is crucial. Like in proposition calculus, when we were discussing, we have a statement can be either true or false. Element can either belong to set or doesn't belong to set. Okay, so just know that these are the limitations of these structures which we are using. So let me go forward. So sometimes there is one more thing before we just leave this set. I will just mention it because that will also play a crucial role. So something is called membership table. Or otherwise it is also called characteristic function. Okay. So for example, if an element, if a member belongs to a set A, then we write its membership value to mu A at particular x is 1. If an element doesn't belong to the set A, then we write that its membership value is 0. So this is one more thing which we will be using in future. We will be needing in future of the today's talk. So remember that there is something called characteristic function which shows us whether a particular set is inside or outside. So it can have only two values, 0 and 1. Okay, and then we have one more thing, like we have when we take a Venn diagram once more. So there is a principle called exclusion inclusion principle. What does it says is that, see, if you take A union B means whatever is available in A and B together. So when you think, you can understand that this comes twice. So this principle says that by the way, if a set A is given as say A, B, C, the number of elements in A is called the cardinality. Cardinality of A, and it is represented as like this by parallel lines around it. The number of elements. So in this case, actually, cardinality of A is 3. Okay. So cardinality of A union B is equal to cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay. So this is called the theory of inclusion exclusion. Inclusion exclusion. Okay, principle of inclusion exclusion. Principle of inclusion exclusion. So this is about the characteristic function and about sets. The last thing which we will discuss before we go back to the slides is something called propositional functions. Okay, so we have studied about functions when we study our maths. We have studied about functions. So let us see how that function concept can be generalized. So we have something like, we have seen that this represents a function. The function can be of any value. It can have any functional form like an algebraic thing. So we are normally familiar with a function like f(x) is equal to 2 to the power x plus p log x or something like that. This is a function. This is an algebraic function. Speaking about propositional function. Propositional function. Okay, so say propositional function which says that x is an integer. Okay, so so px. So what are the elements of what can px take? 5 is an integer. Okay, 7 is an integer. 25 is an integer. 40 is an integer. But 2.3 is not an integer. Okay, so there are certain objects which belongs to the set, There are certain other objects which doesn't belong to this set. The set of all objects which belongs to this set is forms the domain of discourse for this particular propositional function. So in this case, with respect to this particular px, x is called a variable. X is called a say free variable because it is free. Free variable. Why it is free, we will understand it shortly, but it is not, we will see. For the timing, just remember that it is called a free variable. The domain of discourse, which is the domain of discourse, which is the set of all the values which satisfies this propositional function, and actually px is the proposition, px is the sentence of the propositional functions. Okay, so that is, so a propositional function can be true or false. I have said you, for example, P7, that is P of x when x is equal to 7. So this is true. But P 2.3, that is P of x when x, this is false. P of 7 is true, this is true, but this is false. So propositional function can also take up to two values, that is either true or false. Then there are certain quantifiers. So we should learn about quantifiers. What is quantifiers? So we have quantifiers like, this is a quantifier called universal quantifier. Universal quantifier. Why it is called universal quantifier? Because if you put like this, P of, this is read as for all. For all px. Okay, here I did something like for all x px. So this is universal quantifier for all x px. So this is true for all x. Okay, that is called universal quantifier. And then there is called something like here. This is called existential. Existential quantifier. So there exists x px. Okay, so a particular instant exists. There exists x px. This is for all x px. So remember that. And then in all these cases, see, whenever we put there exists x px for all x px. So in this case, all this whenever there exists and for all comes, these types of variables which are here, this variable becomes a bounded variable. So this is the difference between a free variable, which I have discussed just a few minutes back, and the bounded variable. Okay. Okay. Then we have, so all these things are fine. So we have so with your background in sets, what we have discussed, with your background in first order propositional logic, what we have discussed, with your background in propositional functions, which we have discussed, we will say what is there is something called as a predicate calculus. It is not our normal calculus. It is something, it is just the name is called calculus because it calculates based on certain inferences. So there are certain actions for that calculus. So what is that? It says that all statements that are considered, all statement formulas, for example, formulas like P and Q implies R, negation of this. So this is the formula. So the P, Q, R and all are this one. So this full thing is the formula. Okay. So don't forget about for the time being that a plus b whole square is equal to a square plus 2ab plus b square. Like that only some equality should be there for a formula. No. So this statement is a formula. Okay. Then for example, if you take a predicate which, so this we have considered as a single valued predicate. Like for example, x is an integer, and one more we can put something like for all x y, p, x, y. So what is that? X is an integer and y is even number. Okay. So like that, we can have a multiple number. It can be a tuple of n or any numbers. Okay. So we can have like for all x1, x2, dot dot dot, xn, p of x1, x2. So this is a predicate, n valued predicate, a tuple, x3 and so xn. So this is also a formula. So that is a formula. This is a formula. Anything which is formed, see, E is a formula. So let us call this as A. This is formula. A is a formula. B is a formula. Not A is a formula. A and B is a formula. A or B is a formula, or any combination of all these things is a formula. There exists X, A, X is a formula. There for all X, X, there exists X, X is also a formula. So whatever are there here are all formulas. So whenever we write a combination of statement, that is a formula. Whenever we put existential quantifier and write the proposition, that is a formula. When we use the operators, that forms a formula, and all those things are all formulas. And similarly, we have other inference rules which are extended from the propositional first order propositional logic to these propositional functions. So we have those inference rules, which I will again just for completion state it, so that it will give a flavor to that. Let us see. So we have something like for all x, px is true. If this is true, then p is true where a is arbitrary. Arbitrary means it can take any value. So for all x, px is true, then pa is true. So this is called universal specification. This is a rule. So these are inference rules, further inference rules. Okay. So we have now if PA is true, where A is arbitrary, then for all x, px is true. This is called generalization, universal generalization. So like that we have universal generalization, universal, then we have there exists x, px is true, then pa is true. So this is universal specification. You are specifying there exists a x for which px is true, so pa is true. So you are universally specifying universal specification. Okay, and then we have existential generalization. If Pa is true where A belongs to universe of discourse, then there exists x, Px is true. So this is called universal generalization. Okay, so we have this so many rules. Then we have modus ponens, universal modus ponens, universal modus talens, and all those things. And based on all these things, actually, there are different types of proofs. Proof means when you make a logic, you are actually getting a sentence as a deduction. Okay, so whether the sentence or whether you have inferred certain things, whether that is correct, if you want to prove it, if you want either yourself to prove it or a particular machine to verify that whether the inference is correct, you require a proof. We are familiar with proof. We do so many proofs in our mathematical things in physics and all those. So we prove it or we deduce it. So we prove it. So how do we prove it? So we can have there like direct. You have a number of axioms and you get it one after one directly by the rules, inference rule, and you reduce it, you get a proof. That is called a direct proof. So there are different types of proofs. So I just write it down. So we have direct proof, then we have indirect proof, indirect proof in the sense that if you can prove that a particular P and Q are there and P and Q are there, and if you prove that Q is not true, then we can prove that P is true. In that way we can have indirect proof. Then proof by contradiction is there. You assume the negation and prove that it is false. Proof by contradiction. And then we have proof by implication. That is, I'll show you. Proof by implication. So, for example, if you want to prove that two sets are equal, what we have to do that we show that A is a proper subset of B, A is a subset of B, B is a subset of A. And if these two are valid, then we say that A is equal to B. So it is a by implication. Then proof by equivalence statement. So there are different types of proofs, and one more thing is that one symbol is used. We will be seeing it. There is something like LS system, where for a machine system, actually, the literature says LS system. These are the set of rules, like whatever inference rules we have. These are the set of rules. And these are the set of symbols. So let us now move back to the slides, and we will continue it from there. Okay. Yeah. Yes. So we have done up till here. So we know it. Now, based on whatever we have discussed, let us continue it. So there is something called, there are different propositions and there are properties of proposition. There are something called satisfiability. For example, for every interpretation, there is something for which it is true. So there is satisfiable. Then there exists no interpretation for which it is true. It is called a contradiction. For all interpretation, it is true. That is more valid. That is also called tautology. Then true for every interpretation, that is called equivalence. So logical consequence. These are the different properties of propositions we have, and all these things actually we have seen. So I will not.
Equivalence and valid.
Yeah, tell me.
What is equivalence and valid?
Valid. Yeah, valid is true for all interpretation. Okay, if it is true for every interpretation, like we have it, yeah, it is called a valid. Okay. Okay, so now we have a few more definitions like formal systems. I have already shown you what is an LS system and why it is sound. If it is sound, if the statements can be derived from LS system in a logical. So we have a set of rules, we have a set of symbolic statements. So if whatever is in the statements, all can be derived from the rules. From the statements, we can derive other statements. It is called a sound system. Okay. Similarly, if an inference procedure is complete, if and only if the logical sentences logically implied by LS can be derived using the procedure. So anything else, if you want, if you can derive it from the whatever inference rules are there, it is said to be a complete state, a complete system. So we have soundness, we have completeness in formal. So what is a formal system? A formal system is a structure where we have a set of rules and a set of symbols, and this is used for knowledge representation. Okay, so these all things we have already done. So there are different types of non-deductive and inductive, analogical reasoning, and all those things are there. So we will not again go into detail because then it will take a lot of time. So abductive, you can say that inference, you can make some observation and make a inference out of it. These are not non-deductive. You can deduce it through. So there are various ways in which actually inferences can be made. This is also one of the better where it is not deducible, where it is not symbolically possible. So there are some heuristic methods which will be used. There are analogical reasoning. So we reason, our humans reason using all these methods also. We inductively. So we see a small area and we make forecast about, we predict about a bigger thing. So for example, we see that part of the sky is cloudy, we say that today is a cloudy day. It may not be like that, because if you travel some 2 kilometers, it may be very sunny, but it may not be true. So we are giving an error. So we inductively infer that may be true, may not be true. So now we are always in the bivariate logic, that is either true or false. That is the thing. So there are other things. Now, see, there are other things like people use different types of things with inconsistency. When we speak, normally see that you have seen in that video, one person was speaking with some child and all these things. So when he was speaking, actually, he was interacting with the child. You can't expect a child to give a completely valid, informative sentence. No, he will think something, he will say something, and if the system understands that, okay. So with inconsistency and uncertainty, if it can process the information. So that is showing certain signs of intelligence. So there are various types of non-monotonic reasoning. So in that actually it deals with, it is a part of the classical logic. Classical logic is that true-false logic that we have done bivariate logic, truth values only two, either true or false or 0 or 1. So that is the way actually. So it includes certain methods for dealing with incomplete information. So that is called monotonic reasoning. And there are other things like default reasoning, closed world reasoning, and all those things. And so these are all various methods. So I will just go through some of the methods, because we will come to the our main talk today. So we have now that modal logic. The modal logic is one more type of logic, not like a proposition logic. It deals with actually, we speak about certain situations which we are aware of. For example, we are aware of a certain situation in Calicut city, but we are not aware of a certain situation in a nearby city like Kochi, or maybe if connectivity is not there, if we don't have video TVs and all those things, we can. So they are different worlds actually. They can be thought of as different situations. So to do it possible, or some situations are possible which are not in reality. So in those types of logics are developed by something called as a modal logic. And then we have some temporal logic, by it deals with something like present, past, it is happening, it will happen. So like that, temporal aspect, time aspect is taken as temporal logic, and fuzzy logic. So we will discuss something about fuzzy logic, and which is also used for natural language processing. So we have seen that there are other things. I will just rush up with this, like procedure-based, rule-based system, like if-then systems are there. And there are certain procedural attachment attached to that. You can see that in the slide about rectangle and square, certain informations are given. And there are network systems, for example, semantic nets, like here it is given about a person, about its height, weight, and what are its attributes and all those things. So this is a semantic net of a knowledge representation of a person. And then there are structured representation where you put frames, like if you want to say about its birthday party. Now we understand what is a birthday party. Now how do you make a machine to understand what is a party? What is a birthday? First you have to make him understand. What is a party? What people do in a party, you have to make it understand. So you have to present the data with different definitions. So that is what is given in form of frames, different types of frames and scripts. And then when we have certain situations which are random situations which we have no control over it, so they are called random. It can happen, it may not happen. So in that way we use probabilistic reasoning. So there only we will use probabilistic. Now that is one of the difference between probabilistic reasoning and fuzzy reasoning. So what is fuzzy? Now we will come to it. So what is fuzziness? Now fuzziness is something, when we deal with people, when we speak about certain things, when we say about our opinion, many of the times actually we are very vague. We say that, for example, a girl is beautiful, this climate is very cool. So for example, very cool or the student is not doing well. Now, what is the meaning of this not doing well? Very cool, beautiful, or very intelligent, or very tall, or less scary. So, like that, these types of things. Now, when it comes to the literature, now how to formulate this type of concepts, this type of knowledge to an expert system. So here one new logic was proposed, and that is called fuzzy. Now fuzzy is in not saying we are not about unsure about things. It is a different type of logic where actually we put truth as intermediate values. We will be partially true or membership will be partial. So something of that sort. Okay, for example, Boolean algebra, Boolean logic, what we were dealing with up till now, true false logic. That is called Boolean logic. It makes a far distinction, means a sharp distinction. But fuzzy logic actually reflects how we people think. So that is a more realistic logic. And this was actually proposed by it has people have been thinking about different ways, but people started thinking. I like Jan Lugaczewski. He thought it in 1930, and he has all made about a three-valued logic or n-valued logic, but they could not come out with a fuzziness as was done afterwards, which I will be discussing. So this is a many-valued logic. Indian logic also, we have a lot of Indian logic, Jain logic, Nagarjuna's logic, and all those things. So we have in Indian literature also, Indian philosophy also, a lot of different types of logic. So this Jan Lukaczewski's logic led to a new theory called possible words. Then Max Black was there. He tried to model vagueness. When we say something vague, he tried to make a theory about vagueness using some probabilistic situations and all those things. So then came in 1965 Lafayette. He did a mastermind work actually. That is the founder. He is the master of what is called fuzzy logic, fuzzy sets, fuzzy interpretation. So he is the inventor of that many-valued logic. So what does he say? What is fuzzy logic? He said that we don't think in terms of concrete things. Whenever you yourself, if you sit and think, you will not think precisely. No? You can't say that definitely tomorrow this will happen. You can't say that, because in fact after 5 minutes what will happen you don't know. We will speak in terms of vagueness. We will speak in terms of some uncertainty will be there in our interactions. So how to deal with such type of thing is a part and parcel of fuzzy logic. So fuzzy logic will start with new tools which it will discover, which it has proposed, in which actually it will give degree of membership. We have membership or thing as 2, 0 or 1. So we have the different degree of membership. That we will just see. Instead of just 2 values we have. For example, you can see in this particular slide we have a Boolean logic, we have a multi-valued logic. The Boolean logic makes either white or black. Multi-valued logic, so there are various shades, and you have to define actually when you can say it is black, when you can say that it is more black, it is mid black, it is not black at all, or something like it is whitish or something like that. So it gives a range of values. So now let us now just go to the whiteboard once again and just see how do we actually understand this fuzzy type of thing. Okay, so yeah. So when people started understanding fuzziness, as we will discuss now, so people started developing fuzziness. They have discovered that there are normal sets which we were speaking about. They are called crisp sets. So their crisp sets are something where actually the characteristic function has only 2 values. Either it belongs to the particular set or it doesn't belong to that particular set. So it has only 2 values, either 0 or 1. Now slowly people started actually defining new terms in terms of fuzzy sets. So that we will see what is a fuzzy set. So characteristic function, once again back to characteristic function. So up till now we will just revise it. We have already done it. So mu ax. So we have said that it is 1 if x belongs to A and 0 if x doesn't belong to A. So that is one thing. So remember that. And then we have something called as a convex set. What is, so if you are dealing with something like, if you are dealing with two numbers, say n-dimensional representation, say R1, Ri, I belongs to capital N, and say Sj, J belongs to capital N. So it is something like R1, R2, Rn, it is a tuple, and similarly we have S1, S2, Sn. So we have, if you take this cardinality as same. So if we define a new variable which says that it is lambda r plus 1 minus lambda s, where lambda belongs to the interval 0, 1. So this interval, this is called a closed interval. So any line on a number line, if you have 0, 1, when you include this 0 and 1 together and take this particular interval, this all the numbers in between, it is called as a closed interval. If you don't take 0 and you take everything else, it is called a semi-closed interval. If you don't take both 1 and 0, it is called open. So this is closed interval, this is open interval. Just remember that. So this type of thing, if T also belongs to that particular set, if R and S belongs to set A, and if this T belongs to set A, then it is called as a convex set. So now, what is the membership function? So when we speak about membership function, we give certain degrees. It's an intermediate between 0 and 1. So it is partially, like when we say about very good, when we say about young, when we say about old, when we say about middle age. Now, how do we represent all those things with respect to the sets? So we do it with respect to the characteristic function, and there are various formalism for defining the characteristic function. So I will just show you some of the examples which can be used. So characteristic function always say mx with respect to a set A or a variable x, it always maps to this closed interval 0, 1. So maybe something like mx, ma x is equal to say 1 by 1 plus 10 to the power 10x square. So this is for example, if you take the value and if you have one more characteristic function mu y is equal to 1 by 1 plus 10x square whole square. Now you see that this goes in a particular rate. When you square it, this goes faster. Okay, it goes faster. So in this case, actually, in the sense that you have for each element a particular degree to which each element belongs to the set. Now this is quite different from what actually we had from a Boolean logic, Boolean way of seeing it, a two-valued logic where we have only either 0 or 1. So you need not always map it to 0 or 1. People have actually extended it to 0, L or something of that. So any interval you can map it and you can get different types of characteristic function. So let us actually take an example. We have an example so that you can understand the concept of this characteristic function better. So let me write some values. Yeah. So we have, say let us take variable age. Let us call this variable x as age. Its name is age, and let us write some values like 5, 10, 20, 30, 40, 50, 60, 70, 80. Okay, let us stop there. So now let us take a fuzzy set. Let us write some fuzzy sets labels. Fuzzy sets labels. So we will call it as infant, adult, young, old, and so on. So only these are the labels which we have. So the thing is that each person, so we have to make a table to show that with what degree each person, each of these age groups, say 5 years, 10 years, to what degree it fits in either an infant or an adult or a young person or an old person. So let us make a matrix like this. So let us write the value of x here, and let us write that infant, adult, young, old. And we have here, so in values of x we can 5, 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, so we have, say infant, it is 0, it belongs, when you are 5 years, infant 0, adult 0, young you put 1, old you put 0. This is an example author has given like this. So then we have 10, for 10 years old, we have infant 0, adult 0, again young 1, old 0. Then when it becomes 20, we get infant 0, adult becomes 0.8, okay, young becomes 0.8, and old becomes 0.1. So he has become old, but it is only, his membership is only 0.1. So that is degree of membership. He belongs to the old group only 0.1. Okay. Similarly, we have 30. So we have here 0, we have 1, we have 0.6. So now he is 0.6 and 0.2. So you see how the membership is changing. His 0, 1, 0.2, and 0.4. Then we have 60 when he becomes 60 years. So 50 years, it is 0, 1, 0.1, 0.6. Then we have 0, 90 is not there, 0, 1, again 0, 0.8. Okay, then we have, when he's 70 years, infant is 0, adult is 1, young is 0, and old is 1. And when he is 80, infant is 0, so it is same, 1, 0, 1. So you see that how the membership values with respect to the attributes change. Okay, so based on this, whatever we have written here, we have an age group, we have 4 labels, and we have the membership with respect to the age group, to what degree they belong to that particular labels. These labels are actually sets, and in this age group, the membership to these sets are actually certain degree with which actually these elements are, these age groups are are having membership in these sets. So now there are some technical things which have been discussed, which have been devised to work with all these things. Something is called, we'll just discuss, there is something called as a support. What is support? Support is support. Now support is the set of all those values, all those membership values which are greater than 0. Support of the set, if you call the support of infant or support of any set A. What is set A? So for a set of all those values, all those x which belongs to the given set, for which the membership value is greater than 0. So that is called support. Similarly, you have, so we have, for example, support of infant. You say here there is no member. So support of infant is null set. It has no. Then support of young adult. So you have certain degree of certain age group belong to young adult. So you have certain things. The support of young adult is, say for example, 5 is there. 20 is there. So 10 is there. So like that, you can see that various young adult what all supports are there, for which actually mu characteristic is greater than 0. So how do we represent a fuzzy set? So some fuzzy set is represented as each of these degree with which a particular member is inside a set and it is written in this particular way. For example, if I write fuzzy set, if we write it like mu1, mu2 are the different types of degrees for x1, x2, xn. Yeah. So if you can write this fuzzy set as A is equal to mu1 by x1 plus mu2 by x2 plus mu3 by x3 plus plus mu n by xn. Okay. So it is not pure addition. You should understand. This is just a representation. Sometimes actually it is represented as summation of ui by xi. Again, this summation is not our addition summation. Or sometimes if it is a continuous variable, it is represented as integral of say ui x by x xi or something like that. So these are also not normal integration. So what happens is that these are all representations. So how a fuzzy set is represented with respect to a support. Support is the set of all those variables which has a degree greater than which has a association degree greater than 0. So with respect to that support, any fuzzy set can be for each element. For example, in this fuzzy set of adult, see in this fuzzy set of adult, how do you represent fuzzy set of adult? We can write it as adult. Adult can be represented as something like we have first set is 5. So membership is 0 by 5. Okay, you can write it something like plus 0 by 10 plus 0.8 by 20 plus 1 by 30 and so on. So you can write it like this up till the end. So that is the way you represent a fuzzy set. So any doubt in all these things up till now? Any doubt? So for each fuzzy set, the maximum value of characteristic function gives the height of the fuzzy set, and if the fuzzy set for any of the characteristic value reaches the value 1, it is called as a, for any one variable also if it reaches the value 1, it is called as a normalized fuzzy set. Then if it is not reaching the value for all values, or at least one value it doesn't reaches, it is called as a subnormal fuzzy set. So in this way actually we can we have there are tools to actually for definitions with which actually they have defined the union, intersection, complement and so on. So a fuzzy full set has been developed with respect to all those things. And then as you can see that all this fuzzy, if you draw it with respect to variable and diagram, for example, it is not, see, bivariable logic, either it will not be there or suddenly it will increase. So like this representation is there. But in fuzzy set actually what happens is that if you have a particular value, it will increase, it will remain, and then it will decrease. So these are the so various ways actually we can represent fuzzy sets. A triangle, it will go and it will come back. So based on this actually we have fuzzy numbers. Fuzzy numbers are fuzzy sets which satisfy certain characteristics. So we have fuzzy relations where we define a relation. Binary relation, you know what is a binary relation. For example, if you take the Cartesian product of two particular sets and you map it to the a particular value, you get the binary relation. So similarly, you can define the fuzzy relations. And the way we have studied the propositional logic, so you can define the various truth values. So we have like linguistic variable, like something like tall, short, close, open. So these are called linguistic variables, and there are certain what in literature it is called as the edges of linguistic variable, like very short, very tall, smooth, very, very smooth. So all these things can be actually represented. This knowledge can be represented using these types of apparatus which are called fuzzy sets. It takes certain time. Actually in one class we can't. We have all the materials, but I can't teach you everything in this one class. We have to split it, and if I teach you also you may not appreciate, because everything put together it will be difficult for you to learn. But you can understand one thing, that what it is trying to do is that it is trying to come out of the convention where actually it has it was for a bivalued apparatus, bivalued representation, in or out, true or false. Now the truth values are maybe, yes, partially correct, like that what we have seen. And we have a mathematical apparatus like fuzzy set theory, which has been proposed, and which is the way actually which is used. So with this a brief introduction, because I thought we will be doing a lot, but anyway, so as I said you that, so this is the way of representing fuzzy numbers. Fuzzy numbers can be represented in various intervals, since it is not crisp, so it is having a rise and a decay, and there are certain overlaps. You can see that in that particular table which we have made, there are certain overlaps. So all these things, and there are certain other concepts like fuzzy cuts, level, and all these things. I will not go into all these accounts. So with that, actually, I will do one thing. I will forget about all those things, and so I will come to this particular slide. This is quite interesting in the sense that actually you are seeing that different types of logics which has developed during 1930. You have seen that we have seen Lukasiewicz logic. He has made the logic with the introduction of a 3 value, that is 0, half, 1. So how the different connectives, when you use the connective between A and B, if A is 0, B is 0, A conjunction B, what is the value? So if A is 0, B is half, A conjunction B according to Lukasiewicz logic is written here half. So you see that whenever we are dealing with any non-partial numbers, they both are matching with the formal logic. But there's 2 valued logic. But when we are dealing with part, it is different types of. This is one logic. This is another logic. Bochap logic, Keel logic, Hating logic. So there are different types of logics actually, and they have developed their full apparatus, mathematical apparatus for representing those. So all those things are there. So fine. So I will do one thing. I will just recap. So I will start from here. Sorry. So there are various applications of this fuzzy set theory. It has applications in computer like fuzzy. We have controllers, fuzzy controllers. They control in a fuzzy way. There are something called fuzzifier, which fuzzifies and takes all other things into consideration, and then after operation it defuzzifies and give the output. Then there are in robotics, it has to take care. We have already seen a part of it in the video. And there are a lot of other applications in that. So basically, a fuzzy logic is something which tries to quantize partial information, vague thing, uncertainty, and bring it to the knowledge domain, bring it as a knowledge representation tool. So we have fuzzy logics where you can see that certainly yes, possibly yes, cannot say. So all these things can be actually formalized using the fuzzy logic. So we use fuzzy logic because it can be used for controlling machines, procedural reasoning, acceptable reasoning, and all those things. Uncertainty, it can deal with uncertainty. And the architecture, as I have already told you, that there is something called a fuzzifier, and it uses certain inference rules which we could not actually fully discuss it today, because it will take some more time to discuss it. And it has intelligence, and it gives device bias, and it gives crisp input, crisp output. But if you have a fuzzy structure inside, you can deal with a lot of different types of things which otherwise would not have been possible. So membership functions, we have already seen what is a membership function and how to represent it, input and the membership values, and how the probability theory. Probability only deals with random events. It can't deal with everything. Is not random. We don't always fall under random category. So there are a lot of well-planned things. Tomorrow exam will be there. That is something like it is not a random thing. But then suddenly something occurs, a calamity occurs, the exam gets cancelled. So we can't be sure that exam will be there tomorrow. So in that way, there are certain uncertainties. So that is nothing to do with randomness. So probability theory can't be used in those stages, and we use something called as a fuzzy logic in those stages. So applications and all are there. So it has a lot of advantages, as we have already seen that it has a lot of advantages. But then there are certain disadvantages also, where it is not always because it is a developing subject. People are working on it, and there fine tuning are required, and many aspects actually it has to be integrated. A lot of people are trying to integrate it, so it is a developing subject. So that actually gives a disadvantage to it, because it is not yet complete in the full sense to be used everywhere. It is theoretically it is developing, practically people are trying to use it. So in that way it is going on. So that's all. And if you have now any questions, you can just ask me before we conclude.
Okay, so if there is no question, I think we conclude here. Thank you, thanks to all of you for having come here and yeah, thank you. Okay, thank you. Bye.